Good morning, gentlemen. Today is Wednesday, June the 2nd, and today we are going to continue our discussion of modern physics. And we're going to do so by talking about what we call um, uh, atomic spectra. Now, atomic spectra is something that you've actually talked about already in Mr. Leonard's class, chemistry class, last year. And essentially what it means is that when you burn a chemical in a fire, right, and you did a lab on this, you took a little wire loop and you dipped it in a chemical with whatever was in it, and you burned it. And you noticed that each specific metal especially gave off a certain color. Lithium gave off red, and copper gave off blue, green, and so on. Okay, these are what's known as atomic spectra. And I don't know what kind of detail Mr. Leonard went into in your class last year, but we do know that this relates to physics as well, specifically modern physics. So this all ties into what we were talking about in the last lesson, where when an electron jumps from one electron shell to the next electron shell, it emits I'm going to move myself over here. It emits a ray of light of a very characteristic wavelength and frequency. And this is what's known as the atomic spectrum. Now, the atomic spectrum of a given atom is something that can be used in order to identify the atoms that are found in a given molecule. So if you've got an unknown molecule, you can put it in what we call a spectrometer, which will essentially heat it up until it burns, and then allow the rays of light to be captured and analyzed, and we can determine the frequencies and wavelengths of those rays of light, and that can give us an idea of what the identity of a given atom or number of atoms that are found inside a molecule are. So the basic principle behind how this works is as follows. When excited electrons fall back into the ground state, so from a higher energy level back down to a lower energy level, they have to give off that energy. So they emit energy. And that energy is given off in the form of light. Now, as you well know, each color of the rainbow has its own characteristic frequency. And so we refer to this as the emission spectrum. All right, the light that's given off by an atom or an electron, as it jumps from a higher energy level to a lower energy level, is called the emission spectrum of that particular atom. And again, this can be used to identify unknown molecules. Right? But you put them in a spectrophotometer or a spectrometer, and you can find out what's in there. Now, I do have to mention that this can also be done with what we call absorption spectrums. If you hit an atom with a very specific color or wavelength of light, it will cause the electrons in that atom to jump to very specific energy levels. And we can measure that as what we call the absorption spectrum. Now, how do we do all of this? Well, the formula that's currently on the bottom of your screen is what allows you to be able to do some calculations with this. And this formula is found on the reference tables in the modern physics box. And you'll notice that the second formula is the one that's on the screen now. The energy of a photon is equal to the initial energy minus the final energy. Okay. Now, over the course of many years, scientists have been able to determine the amount of energy that it takes an electron to remain in a very specific orbit around a nucleus. All right, and this is true for each of the various atoms that you find on the periodic table. All right, and so many of these are well known. And so how do we then use this information in order to calculate the things that we need to know? So example 5 says a hydrogen atom absorbs energy causing its electron to move from the innermost energy level, which hopefully you remember from chemistry is n equals 1, where n is the orbital or the shell, all right, the energy level, to the second energy level, or n equals 2. And you are given this task. Determine the energy of the first and second energy levels and the energy absorbed by the atom. Well, the second part of that question is obviously the formula that we talked about on the previous page. However, the first part is a mystery, or is it? Well, if you get out your handy-dandy reference tables once again and turn them to the third page, you'll find a section there called Energy Level Diagrams, all right? And notice there are two atoms here, hydrogen atoms and mercury atoms. Now, example number 5 referred to the hydrogen atom, so we'll go back here. And we had to find the energy levels for n equals 1 and n equals 2. Well, for n equals 1, all right, and you can see n equals 1 right here, all right, the amount of energy is 13.60, negative 13.60, and the units are given in electron volts, all right? You can see that right here, all right? Energy in electron volts, negative 13.60. Now, for the second energy level, you can see right here, negative 3.40. Sorry about the phone ringing there, guys. Now, and that is the second energy level. Okay? All right. Now, so how do we do this problem? Well, the initial energy level here is, we know, negative 13.60 electron volts. Oh, it's a courtesy call from Hannaford Pharmacy. And the second energy level, n equals 2, had an energy value of negative 3.40 electron volts. Okay, so the energy of the photon is going to equal EI minus EF. So negative 13.60 minus negative 3.40 electron volts. All right. Doing the arithmetic there right quick, you're going to end up with negative 10.20 electron volts. Now, although I didn't ask you to do this, I'm going to point out one more thing here. Electron volts is not the standard unit of energy that we typically use in calculations like this. That unit would be the joule. And so if you go to the front page of your reference tables on the list of physical constants and you look up the value of 1 electron volt, whoops, right there, okay, and move over, you'll find that 1 electron volt is equal to 1.60 times 10 to the negative 19th joules, okay? And so I'm going to take this and simply multiply it, negative 10.20 times, whoops, 10.20 times 1.60 times 10 to the negative 19th joules, and that's going to give me 1.63 times 10 to the negative 18th joules. All right, so these two numbers are equivalent. All right, the negative 10.20 electron volts, and the negative, it should be 1.63 times 10 to the negative 18th joules. All right, so those are equivalent terms. All right, but the answer, the answer to the question, come on, the answer to the question is this right here. Okay, so let's move on to a second example, one which is just a wee bit more complex, all right? So we're going to go from this to the next, and there's several parts to this question. So again, we're going to use hydrogen. So an excited hydrogen atom drops, this should say drops an electron from the third energy level, n equals 3, to the second energy level, n equals 2. All right, so you're asked to calculate the energy. We know how to do that, right? We get out our reference tables, we look at the energy levels, we take the difference between them, and we can calculate the energy. We'll then convert that energy quickly to joules. Now, calculate the energy and the wavelength of the emitted photon. Okay, the wavelength. That's an interesting question. And then finally, we're asked to calculate the value of the color, or the color of the light. So let's start. We're going to make ourselves a laundry list. All right. So the energy level of the photon in this case is going to equal the energy of 3 minus the energy of 2. Okay. And again, go back to your handy-dandy little reference tables on the third page, the energy level diagrams, and you'll find that the energy level for level 3, n equals 3, is negative 1.51 electron volts, minus the energy level for 2 is negative 3.40 volts. And if you take the difference between them, you'll end up with positive 1.89 electron volts. Okay. Now, 1.89 electron volts times 1.60 times 10 to the negative 19th joules per electron volt is going to leave me with a value of 3.02 times 10 to the negative 19th joules. All right, so there's my energy. Okay. Now, the second part of the question asks you to calculate the wavelength of this light that was emitted. So for this, we're going to go to our formula sheet once again. And the very first formula on the modern physics page is the energy of the photon equals the Planck's constant times the frequency, or Planck's constant times the speed of light in a vacuum divided by wavelength. That's the one that we want. Okay? So the energy is going to equal H times C over lambda, and therefore lambda is going to equal H times C over energy. Now, Planck's constant, remember, is found on the front page of your reference tables, all right, right here, all right, and that is given as 6.63 times 10 to the negative 34th joule seconds, okay? So 6.63 times 10 to the negative 34th joule seconds times the speed of light in a vacuum. Again, this is found on the front page of your reference tables. 3.00 times 10 to the 8th meters per second. So I'm going to skip the sig figs there. Times 10 to the 8th meters per second. All right, so notice the seconds are going to cancel out right away. Divided by, and I'm going to plug in my value of energy in joules here. So 3.0 times 10 to the negative 19th joules goes here. And so the joules are going to cancel out. What am I going to be left with? My units are going to be meters. Does that make sense? Whoa. Does that make sense for a unit of wavelength? You bet your sweet bippy it does. So if you do the arithmetic there, you're going to get 6.58 times 10 to the negative 7th meters. Now, how in the name of God am I going to find out what color this is? Well, again, turn to the reference tables. And on the reference tables, you've got the electromagnetic spectrum on page 2. And you'll notice that the wavelengths are given on the top, okay? And I've got a wavelength. But the colors of the rainbow are given in units of hertz or frequency. So I have to convert this wavelength to a frequency. And so for this, the formula is the speed of light in a vacuum is equal to the frequency times the wavelength. And therefore, the frequency is going to equal c over lambda. That's going to be 3 times 10 to the 8th meters per second divided by lambda, which is 6.58 times 10 to the negative 7th meters. And if I do the arithmetic here, notice that meters cancels out, and I'm left with a frequency with a unit of 1 over a second, or a hertz. And so the frequency in this case turns out to be 4.56 times 10 to the 14th hertz. All right, now, if you go back to the electromagnetic spectrum deal and look there, you'll notice that red light ranges from 3.84 times 10 to the 14th to 4.82 times 10 to the 14th. All right, and so since our light is 4.56 times 10 to the 14th, we have red light. Okay, and so the answer is that this is the electron emits red light when it when the electron jumps from the 3rd to the 2nd energy level in a hydrogen atom. Okay, so that is example number 6. Okay, now for homework, gentlemen, do please, by the end of the day today, please do questions numbers 5 through 7 on the modern physics homework sheet. Okay, numbers 5 through 7 on the modern physics homework sheet. All right, fellas, so that is it for today. Stay tuned for tomorrow. Have yourselves a great Wednesday.